Welcome. Let's walk through the construction of a suffix tree using the given Rust implementation. We'll use the string ABCABX as our example. The process begins by initializing the suffix tree structure with the provided text. This is done in the suffix tree new function. We also initialize the root node within the build function, which has no starting or ending positions and an empty set of children node, new none. O represents the nodes while full lines represents the edges. In the extend _suffix _tree function, we start with the first character, there. Since the root node has no child starting with A, we create a new leaf node representing the suffix, starting at this character. This is handled by checking the children hash map and inserting a new node if necessary. Moving to the next character B, we find no existing edge from the root starting with B. Hence, we add a new leaf node for the suffix starting with B, again updating the children hash map of the root node. Similarly, we add a new leaf node for the suffix starting with C by following the same process in extend _suffix _tree. Now we encounter A again. There already exists an edge from the root for A. We traverse this edge, moving our active point down to the next node. Since there's no existing continuation for the next character in our traversal, we add a new leaf node. This traversal and node creation are managed by self.walk_down and subsequent node : new calls. We repeat the process for the next character B, following the existing edge and adding a new leaf node as needed. When we encounter X, there's no existing edge starting with this character from the root. We create a new leaf node for the suffix starting with X. This step is similar to the first few iterations where new nodes are created directly from the root. The dotted line signifies suffix links between nodes. As we continue, we come across another A, which requires us to follow the existing edge and potentially add a new leaf node if the sequence does not completely match any existing suffix. Similarly, we handle another B, ensuring all occurrences and substrings are represented in the suffix tree. Another C is processed, where we again ensure to account for all repeated substrings, potentially creating new nodes as necessary. For the new character D, a new leaf node is added to represent the suffix starting with D. This character wasn't present in the earlier stages, so it results in a new branch in the tree. As we reach E, we similarly add a new leaf node, extending the tree to represent the suffix starting with E. Finally, we add the unique terminator $, marking the end of the string. This ensures that the suffix tree represents all suffixes, including those that end with the end of string marker, edge splitting and suffix links. As we encounter repeated substrings, such as ABC and abcab or uptax, the algorithm identifies the need to split edges. This is managed by checking the condition within extend _suffix _tree and invoking a split when necessary. For example, if our active length reaches the middle of an existing edge and the next character in the text does not match, we create a split node. During the splitting process, if we had created a new internal node during the previous phase, we add a suffix link from this node to the newly created internal node. This linking is handled within the if let some last _new node block in extend _suffix _tree. We continue this process for each character in the string. The algorithm maintains active point adjustments, including updating the active node, edge, and length, as well as tracking the remaining suffix count. These adjustments are central to the while self, remaining _suffix _count greater than 0 feet loop in extend _suffix _tree. Once all characters have been processed, the suffix tree construction is complete. We then finalize the suffix links between internal nodes. Each internal node, other than the root, will have a suffix link pointing to another node that represents the longest proper suffix of the string at that internal node. Finally, we output the structure of the suffix tree, printing each node, its range, the corresponding substring, its children, and any suffix links. This is achieved using the print method of the suffix tree struct. The result is a complete suffix tree that efficiently represents all suffixes of the string ABCABXABCD $.